Modern large language models are physically just too massive to run on the hardware most of us carry. A high-performing model can require tens of gigabytes of VRAM, far exceeding the capacity of a standard smartphone or laptop. To bridge this gap, engineers use model compression, a suite of tools designed to shrink these networks. The industry primarily relies on three methods: pruning, knowledge distillation, and quantization. These tools work well in isolation. However, applying a single method rarely reduces a model's footprint enough to fit on consumer-grade chips. The problem arises when these tools are combined. When researchers stack all three techniques to achieve maximum shrinkage, the model often suffers a catastrophic performance collapse. The resulting AI loses its ability to reason, rendering its outputs useless. This failure suggests that the industry has been treating compression as a simple checklist, rather than a system of interacting forces. This misunderstanding keeps the most capable AI restricted to expensive, high-powered cloud servers. To solve this, researchers are now looking past the individual functions of these tools and analyzing how they apply physical-like pressure to a model's data. This shift in perspective led to the progressive intensity hypothesis. It categorizes compression techniques based on their intensity, or how aggressively they alter the model's parameters. The hypothesis proposes that for a model to remain functional, weaker perturbations must be applied before stronger perturbations. Testing reveals that the order of the pipeline determines the quality of the result. Aligning the sequence with the intensity of each tool provides a mathematically viable way to stack these techniques. The process begins with pruning. This method identifies and removes redundant connections within the network, effectively creating a leaner model skeleton. Pruning is considered a weak perturbation. It removes parts of the architecture, but leaves the mathematical precision of the remaining parameters unchanged. The core values stay intact. Because it modifies structure without distorting data, it serves as the first step. Once the skeleton is pruned, the model undergoes knowledge distillation. Distillation acts as a restorative process. A larger teacher model trains the newly pruned student, allowing the smaller skeleton to recover the intelligence lost during the structural cuts. This combination of pruning and distillation creates an efficient, recovered foundation. However, the underlying numbers are still stored in high precision. To achieve the final size reduction, the math itself must be altered. The final step is quantization, the most aggressive force on the intensity scale. This rounds high-precision weights down to 4-bit chunks, introducing irreversible noise that changes the model's internal representation. If introduced early, these artifacts create a physical wall, blocking the training signals needed to learn and triggering a performance collapse. To avoid this, the sequence must be PKDQ, pruning followed by knowledge distillation, with quantization as the final operation. By carving the skeleton first, recovering the intelligence second, and shrinking the mathematical precision last, researchers can compress a model without destroying its logic. The results of this specific ordering are visible in models like Qwen 2.5-3b. By following the PKDQ sequence, researchers achieved a 3.68 times reduction in model size, while the reasoning performance remained nearly identical to the uncompressed original. This sequence allows the model to preserve instruction-following capabilities that were previously lost during heavy compression. Solving the ordering problem enables the rise of small language models, highly efficient variants that match the utility of their larger predecessors. These optimized models remove the industry's total reliance on massive server farms. AI can now be deployed directly onto secure, local hardware. For the user, this means lightning-fast responses and total data privacy. Processing stays on device, meaning sensitive information never has to leave the user's hand. The shift toward local AI depends on navigating the interactions between these compression forces. Respecting the intensity of these tools is what unlocks decentralized intelligence on the devices we carry every day.